This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good afternoon. Thanks for coming to the tutorial lecture. I was just counting you guys, so there's less than 15% of the class here. So the class is close to 300 students. So thank you, I suppose. I would need to send an email to everyone because, look, today I'm sick and I'm turning up for the class and, other students are not. So it's not a good sign, right? So we need to have a sort of working relationship, and I give you, all credit for turning up. But please talk to your colleagues. I will be sending an email to everyone because, for me, if this class keeps dissipating, at some stage it won't make sense for me to continue giving the class. If I'm addressing less than 10% of the class, it just doesn't make sense anymore. So please, encourage your colleagues to turn up. This is optional. I'm just doing this because I feel it would help you. And as I said, I will be sending an email to everyone. So I hope the attendance improves, because if it keeps decreasing, it's decreased very rapidly. If it keeps it decreasing, I might just offer consultation hours then, because it just doesn't make sense. I can just take you for coffee, a couple of you guys, and we just talk over coffee, right? So we will see how we go. I hope that things change, all right? Okay, so in this class we want to talk about Laplace transform. By the way, if I make mistakes, if I, just stop me and raise your hand, because I'm a bit sick, I'm a bit slow, so it's a real struggle for me to stand in front of you right now. So what we want to go through is these worksheets. By the way, you have all these worksheets and solutions. I mean, maybe not solutions, I can upload them, as we go. But the idea is that you work through these solutions, attempt them before the class, and then we will address some of those in the class. Right? Some of them won't be solved, it's just for your exercise, and you will be also pointed to different books with more solved and unsolved problems. So you will have a lot of problems to work through. All right, so today we want to talk about Laplace transform, and we want to learn how to use it more. Right? So we will just go through several examples to learn more on how to use it. So just to remind you, these are the definitions. This is the definition of a Laplace transform. If I'm given a function of time, y of t, I take its Laplace transform, and then I get this function y of s, where s is a complex variable. And by definition, y of s is equal to this integral, 0 to infinity of e to minus st yt. As we are integrating over t, after the integration, we have these limits in the integral, and after the integration, we will only have dependence on s. Dependence on t will be lost, right, after the integration. So this is the definition, and this is the definition of the inverse Laplace transform. So we also saw that this Laplace transform exists only in the domain of definition. And usually in tables of Laplace transforms, you are given domain of a definition, the time signal, and then its Laplace transform. So now, how you can calculate y of s? Well, you can do two methods. You can use two methods. One method is just to directly calculate this integral. So I give you y of t, right, and you just calculate the integral. That's one way of doing it. I'm not suggesting that that is the way to do things, but we will work through one example just so you see that that's possible. So let's just look at this example first, and then we will go to Laplace transform tables. So here's the example. So method one is calculate basically Laplace transform of this signal. So this signal is 0 for negative time. It's 1 between 0 and 1. It's minus 1. I mean, it's not clear here, but this is minus 1. I will just write it here. Right, between 1 and 2, and then it's 0 again after for time greater than 2. So note that because this function is piecewise constant, it is easy to actually calculate this integral, and we will do that in a moment. But I also want to point out one thing. If you think about this function as a sum of step-shifted functions, then you can see that up to this, so between 0 and 1 times, this is really a single step. So if I apply the step function, which looks like this, so it's 0 for negative time and 1 for positive time, well, this function f of t is exactly equal to that step function between 0 and 1. Now, if I see, okay, what is that function equal to on interval 1 to 2, well, I can add to the original step function shifted function, which is now negative, going from 0 to negative 2. When I add something that is equal to 1 and something that is equal to minus 2, I will get minus 1. And then at this point, 2, I can add a third step function, which is shifted by 2, and it would just be, again, the same step function that goes from 0 to 1. Now, if I add these 3 functions, after positive time, I will get 0. Does everyone follow that? So I can consider this as a computation of this Laplace transform of this function in 2 ways. One is directly plug in function into this integral and calculate it. And another one is use this idea that I just described and then use Laplace transform for these shifted steps. So we will do both, right? So let's do the calculation using method 1, which is basically by definition. So how we can write the Laplace transform? Well, it's a sum of, integral. So what I'm doing is I'm replacing f of t, into this integral. But know that f of t is equal to 1 for time between 0 and 1. So I can split the integral into integral from 0 to 1, where I replaced f of t by 1. And then I can integrate from 1 to 2, and then the value of f on that interval is minus 1. And then the value of f for times after 2 is 0. So I can write here plus integral, from 2 to infinity of 0 times e to minus st dt. But this whole thing would be 0, right? So that's where this, I'm just splitting the integral because I have values of the function on each subinterval. And that's it. So now you have to calculate these 2 integrals. We have everything we need, right? So what are those integrals? Well, the first one, this is the integral of an exponential. Know that we are considering here s as a constant. So actually we have minus s is in the exponential. That's why I have here minus 1 over s, right? So this is the, calculus, so there's nothing new here. But I have to, and then I have exponential minus st, but I have here bounds of integration 0 to 1. I have to replace, this one minus that one, right? When I replace everything. Obviously, t is the variable we are talking about. And then I have integral here. Well, why do I have here 1 over s? So I'm looking at this integral. Why is it 1 over s? Because the value of the function f is minus 1. So this minus 1 and minus 1 coming from the exponential would cancel. That's why I only have 1 over s. And then the bounds of integration are 1 to 2. Can everyone follow that? Yeah. Okay, I see nodding. All right, so this is what you get in the end. So I have here 1 over s, right? And then here inside the brackets, I just was replacing the bounds of integration. So I do have here minus e to minus t with a sign minus. And then I have minus e to power 0, which is 1. But everything is minus. That's why this one is positive now. Right? And then I do the same for the other one. right? I just replace the bounds of integration. And that's it. So this is the Laplace transform for this particular signal, right? Are there any questions? All right, no questions. All right, so the second method, I want to just go back. The second method is to do, partial fraction expansion or simply use Laplace transform tables, right? So here, if I have a general transfer function, I can rewrite it using partial fraction expansions and also just use the Laplace transform table. So you can rewrite it in this way if you have distinct poles, and you can rewrite it in this way if you have poles with submultiplicities. We gave formulas in lectures, right? So let's look at method 2, so how to calculate this function using method 2. So we want to transform the whole thing into functions that we can find in Laplace transform tables. Now, look what we're dealing here with. This is a step function, and this function, so this function 1 of t is a function that is 0 for negative time, and it is equal to 1 for positive time. Now, this function here, 1 of t minus 1, is a shifted step function, and it means it's 1 for t greater than 1, so t greater than 1. When the argument here is greater than 0, meaning t is greater than 1, then this function is equal to 1. And it is 0 for t less than 1, meaning argument of this function is less than 0. So that's the shifted function. How about this function? What is this function here? So it is equal to 1 when t is greater than 2. So this function here is equal to 1 where t is greater than 2. It's no longer 1, it's 2, this guy, because the argument here of this function has to be greater than 0 for a function to be equal to 1. And it is 0 for negative arguments, basically when t is smaller than 2. So what is this function looking like? Well, we already talked about that. So this function, so let's see. If I, for instance, just have this dashed line, well, this function here is the first function. Right? That's the step function. How about, what would this function 1 of t minus 1 look like? It would look exactly the same in shape, but it's shifted. So it's 0 for all times up to 1, and then it steps to 1, and it's equal to 1. How about this function, 1 of t minus 2? Well, it's equal to 0 up to time 2, and then jumps to 1, and it's equal to 1. So know that this f function above can be written really as a sum of the step function, then minus 2 times step function delayed by 1, and then plus step function delayed by 2. That's exactly what I was explaining in the beginning, right? So we are just adding to 3 things. So now, why did I rewrite this in this way? Well, I can use linearity of Laplace transform. So I can take Laplace transform of this, Laplace transform of that, Laplace transform, and sum them up. So I know already that, from Laplace transform tables, step function Laplace transform is 1 over s. This is what we know. But what is the Laplace transform of step delayed and by 1 or step delayed by 2? Well, they are given here. And I will just go to Laplace transform tables to show you that you can find these things indeed. So, by the way, here in Ogata, you have very comprehensive Laplace transform tables. So lots of useful formulas. They are more comprehensive than the tables in Goodwin. So let's see, where is the delay? Just looking for delay. So you can have, so here. So this is like a pulse function. What is this? This is basically a function which consists of a sum of only two step functions scaled by some exponent. Now, in our case, we have two pulses, right? So we can use things like this, and note that what's appearing is that a constant times a step function that's delayed by t0 would be really that constant over s times e to minus s t0, where t0 is the amount of the delay. You can read out this from the Laplace transform tables. You need to solve a few examples to know where to look, right? So you need to sort of be able to match these things. But that's basically taken directly from Laplace transform tables. And the outcome is the same. So what we obtain is given here. So by applying directly Laplace transform tables to this term and this term, and we get exactly the same solution as what we did before by calculating directly the integrals. Right. The preferred approach is to use Laplace transform tables because it's more general. Just in this example, we show that, okay, you can do it differently. Yeah. There is a lot of useful problems that are specified here, right, that you can use in Ogata. And I encourage you, just go through these things. You need to remember these things and use them routinely. So you will need to be quick with solving these sort of problems. Are there any questions? All right. Now, let's consider, so we did go through Laplace transform tables in detail in lectures. I just want to go to a specific item. So let's see. Yeah, so just to remind you, final value theorem. So value of your time varying function at infinity, which is limit as t goes to infinity of f of t, can be found from Laplace transform directly by multiplying Laplace transform of f by s and letting s tend to 0. By the way, note that we are looking for a limit as time goes to infinity, but in Laplace domain, in complex domain, we will let s go to 0. Now, we can only use final value theorem if this limit exists. And we said that it would exist if s times f of s has all poles with strictly negative real parts, right? So let's consider an example now of f of s. So here we go. We are given our f of s, but we are asked to find the limit as time goes to infinity of f of t. So what I would like us to do is to try to use the final value theorem, right? So what would be an answer? So here are the options. Which one do you vote for? I seriously did have answers in exam. Answer to question 4A is I want a pizza. That was the answer. Yeah. So I get in other words, I don't care. So you are offered that option here.
Was it right?
No, it wasn't. So which one do you think is true? Is it 0? Is it minus 1/2? Is it infinity? Sorry? Minus 1/2. I get minus 1/2, and I have c. That's infinity. All right. And no one is voting for A or D. Okay? So which one it is, right? So, well, let's think about what is s times f of s. S times f of s is, well, it's 2 over s minus 2, s plus 2. What are the poles of that function? No, I multiply by s, so s and s cancelled. Yes, and then we have one of the poles with strictly positive real part. That spells trouble, right? So actually this is an example where you cannot use final value theorem. And note, look, if you use the formula, so the formula is given here. If I use this formula without checking whether the limit exists or not, I would get minus 1/2. Right? So by applying this formula, you get minus 1/2. Let's just look at, the correct calculation of this. So this function does have a pole in the right half plane, so we cannot use final value theorem. Now, that doesn't mean that you cannot calculate the limit. What do you need to do to calculate the limit? Partial fraction. Yeah, so you need to take inverse Laplace transform. Partial fraction expansions always work, and if you take inverse Laplace transform, you get function in time domain, then take the limit in time domain. You can always do that. All right? So let's do that. So if we do partial fraction expansion, in this case, I have poles at 0, 2, and minus 2, and hence partial fraction expansion would look like this, right? So you all agree, right? So the only question is, what are the residuals? Now, the inverse Laplace transform of this sum would be the sum of inverse Laplace transforms. So this would be, what, a step function, right, multiplied by a, some a. This would be an exponential function that decays because I will have e to minus 2t times c. So this guy would converge to 0. But this guy here, will diverge. Now, where it will diverge, would it diverge to plus infinity or minus infinity? That depends on what b value is. So let's find what b value is. Well, if I just use the formula for residual for b. This is the formula given in the lecture. So I multiply the full, f by s minus 2 because I'm trying to find residual for the pole equal 2. So I multiply by s minus 2, and then I let limit of s going to 2. So this is what I get. The b here is 1/4. In this case, I do not even have to bother finding a and c because the term that comes from this term would blow up and it will dominate in the end. This will go to 0, this will stay constant but bounded, but this will grow unbounded. And the only question is whether it will grow to minus infinity or plus infinity. Well, since we just found b to be 1/4, then the whole thing here is given by this. This is the inverse Laplace transform of f of t. So note, there is this a, I don't even care what a is. There is this term, which is 1/4 e to 2t, and then plus c times e to minus 2. This guy would go to 0 as t goes to infinity. This guy will stay constant, but this guy would blow up to plus infinity. So when I add this term, and that term as t goes to infinity, I will get plus infinity. If this b here was a negative number, then f of t would tend to minus infinity, right? Now, in cases when final value theorem does not work, you need to go to time domain, first take the inverse Laplace transform, find the function in time domain, find it, and take the limit in time domain. Now, when final value theorem doesn't apply, there are several possible answers that you can get. When either you might have that this limit is plus infinity, or the limit is minus infinity, or the limit may not exist. When does that happen? When would limit not exist? So imagine we can't use final value theorem because one of the eigenvalues is with positive real part. S of f of s, s f of s, one eigenvalue is with positive real part. So when would the limit of f of t not exist? Yes, but moreover, we need to have something else. So there would be, so real part of that eigenvalue, or some eigenvalue, would be positive. How about the imaginary part? Imaginary part would be non-zero. What you would have in some cases, you would have that system that has a complex conjugate poles, whose real part is strictly positive. They would look like this. I mean, the response of these systems would, or part of response, would look like this. So this is what we saw today in today's lecture. You remember, if poles are complex conjugate and they are in the right half plane, the response due to these poles would look like this. Know that this limit doesn't exist. It keeps oscillating. It blows up and keeps oscillating. So whenever final value theorem cannot be applied, then you have three possible answers. Either the limit is plus infinity, or minus infinity, or limit doesn't exist. Okay? Questions? All right, let's go through some of the questions that were given in the worksheet. So here are some questions. We will just go through the starred ones. So here is the first one. So what do you think would be the Laplace transform of this function? To help you, I would just give you, so have a look at this. The answer is hiding here. So, and then I go back. So let's put it like this. So what would be the answer? So Laplace transform of this is a sum of Laplace transforms for this, 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 and this. This is the impulse function. So, all right, let's go one by one. What is the Laplace transform of the step function? This is 1, right? So this is the step function. What is the Laplace transform of unit step? 1 over s. What is the Laplace transform of t? It is 1 over s squared, but I have here 2, so it would be 2 over s squared, right? How about t squared? Well, that's basically this thing here, so 1 over, so we are looking at t squared, but this is now times n minus 1 factorial. So in this case, n is what? 3, and this would be then 3 minus 1 is 2. 2 factorial is what? 2. But we want just t squared, so we can take this t factorial there, and we will get the answer, right? So n here would be what? 3. So, and then the impulse, what is the Laplace transform of the impulse? 1. So we just add them all up. So that's the answer. Let's see. Here is the answer, right? So this is just directly 1 over s. This 2 comes from that 2. This 2 factorial comes from Laplace transform tables, because what is given in Laplace transform tables is, you know, Tn minus 1 divided by n minus 1 factorial. So we had to take that n minus 1 factorial here, right? We multiplied and divided by, you know, like n minus 1 factorial, right? So that's where we get this guy. And then we have 1, that's the unit impulse. Easy. This is easy. Okay. How about the next one? So f of t is t plus 3 squared. now that we've done, so how about I give you now this table, and can you just write this next one down? So t plus 3 squared. So this is really what? Like t squared plus 6t plus 9. Can you find a Laplace transform of that? And here are the tables. So what is it? Can you just go one by one? So I can write this as what? T squared plus 6t plus 9. So what is the Laplace transform of just 9? 9 over s. What is the Laplace transform of 6t? Yeah, all right. And then how about t squared? Okay, good. So that's basically what is given here, right? You just first, write it like this, and then just directly apply the formula. Now, the next one is interesting. The next question is interesting. You are asked to do f of t is t times sine of t. T times sine of t. Now, why is this interesting? It's very instructive. So, by the way, I strongly recommend that you pick a book and you always use Laplace transform tables from that book. Maybe photocopy them and always take them to your exam. Because if you practice from one book and then you come to the exam and use a different book, the tables would be different. So you may be surprised that you don't find something which you expect to see in the tables. Every book would have different tables. The notation is different, and what's included in the tables is different. So my recommendation is stick with a single book and bring it to the exam. So you will know exactly those tables, and you will be already sort of familiar with them. I recommend tables from Ogata. You can just photocopy them because they are rather comprehensive. There is a lot of useful stuff there. If you learn to use them, it will simplify your life a lot. Keeps falling. So here is an interesting one. So we have here f of t is t times sine t. So why is this interesting? Because in Laplace transform tables, you can find a rule that really helps in this case. So I just want to find it. Look at this. So Ogata contains basically, this row 12 tells you that Laplace transform of t times f of t is minus derivative of f of s with respect to s, where f of s is just the Laplace transform of f. You see, that's a very cool formula. And by the way, once you learn to use Laplace transform tables, you would be able to use all of these different rules. You see a problem and you say, I can use this, right? But you have to familiarize yourself with the tables. So let's look at then how to solve this problem. Well, what is the Laplace? So what is in our case f? Well, in our case f is sine t, and we have it multiplied by t. So we need to find Laplace transform of sine of t, and then take its derivative with respect to s and put a minus sign in front. That's what Ogata gives you that already, right? You don't need to memorize this, you just need to learn to use it. So here it is. So let's just look at the calculations. So that's what's given here. So basically you are using that rule from Ogata. So Laplace transform of t times g of t or f of t is minus dgs ds. So from Laplace transform tables, we can find that Laplace transform of sine t is 1 over s squared plus 1. I don't need to go back to tables. This is standard, right? And then you are saying, okay, let me apply the formula. So Laplace transform t times sine t is minus d ds of 1 over s squared plus 1. where 1 over s squared plus 1 is what we just found. That's the Laplace transform of sine t. And then this is what you get. So it's just equal to, 2s over, s squared plus 1 squared. So you are taking derivative of 1 over s squared plus 1, so, and you just take a minus sign of that. You need to remember how to take derivatives of rational functions. Do you remember how to do that? So you take this squared, and what then? Derivative of first times second minus derivative of second times first, right? So you will get exactly this, right? But this squared comes from just squaring the whole thing. So this formula here, so this formula here just gives you that with a sign minus, right? That minus cancels the minus you get from taking the derivative. Are there any questions? All right, let's look at the next question. So the next start question is now going in the opposite direction. So it says find the signal f of t corresponding to the following Laplace transforms. So you are given 1 over s times s plus 1. Now we want to find inverse Laplace transform. So here, what would you do here? Partial fractional expansion. Typically, you can't find terms like this in Laplace transform tables. So how do we do that? Well, here it is. So we start from f of s, 1 over s times s plus 1. So we know that that guy can be rewritten as a over s plus b over s plus 1. Now, look, there are two methods in which you can find a and b. The first method is just to write it in this way, cross multiply. So I multiply everything by s times s plus 1, right? And then I would get this expression, right? So note that, this expression here on top in the numerator has to be equal to 1. So obviously a plus b has to be 0, right? Because the numerator here has only 1. And then we also have plus a. So from here we say that a is equal to 1 and b is equal to minus a because numerator here has no s's. So obviously this has to be 0. So b is equal to minus 1. So from here you get that a is 1 and b is minus 1. That's the first approach. You just sort of write it out in this form, cross multiply, and then equate the coefficients on both sides. The second method is to basically apply the formula that I gave you in the lectures. So a can be calculated as s times 1 over s times s plus 1. Why s? Because we are multiplying the f of s by the s minus the pole with respect to which we consider the residual for. So in this case, the pole is 0. We are considering residual for the pole equals 0. So when you have, as s goes to 0, s and s cancels, you just have 1 over, 0 plus 1, that's 1. So that's the direct formula. And then b, you have to multiply by s plus 1, right? And then again, you let s tend to minus 1. Now, s has to tend to the pole. That's the formula that we gave in the lectures. And you get minus 1. So again, we got the same. So the partial fractional expansion is given here, where a is 1 is b minus 1. So now we have to find the inverse Laplace transform. So inverse Laplace transform would be inverse Laplace transform of this, which is what? What is inverse Laplace transform of a over s? It's just a. It's a step function times a. How about this? B over s plus 1? B times exponential to minus t. So that's exactly what you get here. So the whole solution is given here. Yeah. Let's look at the second case. So we have now s squared divided by s squared plus 1. That's the question. So what's special about this case? What do you think? The order of this polynomial and the order of this polynomial are the same. So what I can do is I can rewrite this as a as a rational function that has order here smaller than 2 plus a constant. So if I add and subtract 1 to the numerator, then s squared plus 1 and s squared plus 1 give me 1. And then I have minus 1 divided by s squared plus 1. The first step is to rewrite it in this way, and then that's what you get. So if we do that, f of s can be written as s squared divided by s squared plus 1. I add and subtract 1 simply to rewrite everything as 1 minus 1 over s squared plus 1. But what is this? Well, inverse Laplace transform of that is Dirac function. And inverse Laplace transform of this is minus sine t. This is directly found in tables. Yep?
So is it possible that I think that it is a square differential of the ft?
Square differential, what do you mean square differential?
Because I can change the s squared over s squared plus 1 to s squared times s squared plus 1 over and then 1.
Not sure that I follow. So can you just so you want to transform it into something else that you can find in Laplace transform tables?
Yeah, but I think the answer is a little bit different from that because the answer I get is minus sine t. It's not impose minus sine t.
So this answer is correct. So if you obtain a different answer, then probably there is a mistake. So maybe you can show me what you did, but there's definitely a mistake. Because you always get just a single correct answer. All right. Let's consider another one. So I'm just checking the time. So here is another one. So f of s is now 3s plus 2 divided by s squared plus 4s plus 20. Now note that you can rewrite this whole thing in this way. Why in this way? Well, depending on what sort of Laplace transform tables you have, you would want to bring it back to some of the terms that you can find in the Laplace transform tables. So as I said, there are different Laplace transform tables, and each of you might follow a totally different sort of approach to transform your expression into something that you can find in Laplace transform tables. In this case, I want to just point out that Ogata does have terms that can be written in sort of this form. So I just want to show you. Let me just find it. It's a bit messy. Yeah, so look at this. Look, Ogata has terms like this. Look, omega divided by s plus a square plus omega square, right? And then it has also s plus a divided by s plus a squared plus omega squared. So Ogata has terms like this. So what that step was trying to achieve, so this step going from this expression to this expression, know that now we have this s plus 2 squared plus 16. That looks very much like something like this in the denominator, yeah? Right. So depending on the tables, you would be, using different steps, right? So let's look at the solution now. So what you can do is you can, rewrite things. You take 3 outside. Why you want to, and you want to sort of subtract here a term that you would get. So if I multiply everything by 3, then I will get here 3s plus 6 minus 4. 6 minus 4 would give me the original 2. So when I took 3 outside, I wanted to have here, I wanted to generate s plus 2, I had to subtract minus 4/3 in order to say that this is equal to that. I'm just looking at the numerator. Don't look at the denominator. The denominator stays the same. Why am I doing this? Well, why am I doing this? I just sort of explained. No, look at this term. What I have here is s plus a, and then I have here s plus a squared plus omega squared. So by doing this operation, I generated here s plus 2 and s plus 2 squared plus 4 squared. That's exactly now in this format. You see? But I have this left over of minus 4 over 3. So I split them now. I have 3 times all of this, minus 4, divided by this. Now, this guy now looks exactly like that guy, and the first guy looks exactly like the second guy. And we just apply inverse Laplace transforms. So that's what you get. So this term corresponds to that term, and this term corresponds to that term from the tables, right? I would upload these solutions so you don't have to take photos. I mean, if you want to take a photo of me, that's fine. I did actually have students taking photos of me, so without me knowing, actually. So I don't know why, but I did have that. So are there any questions? So this is so it's getting more complicated, but you need to solve a few examples to get the hang of it. And as I said, Ogata's tables are quite comprehensive. I recommend photocopy them and then solve those recommended problems. We have some problems in the worksheet, and we also recommended some problems in Ogata's textbook. Ogata's textbook has solved examples and has unsolved examples. If you do all of those, you will be good, right? You won't have problems with Laplace transforms anymore. All right, so here is another one. So this is the question. So you are supposed to find the inverse Laplace transform of this guy. So now this thing is different. Why? Because we have here repeated pole. We have repeated poles. So we need to use residues, formulas for residues for repeated poles. Right. Now these are a bit more complicated than what we had before. But look, one way, direct way to do it is to say, well, this thing here will be really a sum of terms like this. B1 over s plus 1, B2 over s plus 1 squared, B3 over s plus 1 to power 3. You can cross multiply everything and compare the like coefficients. So that's one possible way, right, to obtain B1, B2, and B3. But that's not the only way. You can also use directly the formulas. We are running out of time, so I will just leave it at this. And yeah, if you can work through the rest of the questions yourself, that'd be great. By the way, I mean, if you just go, what's interesting maybe to say is just, I want to just show you the solution. Once you find your, B1, B2, and B3, so they are given here just by the first method of equating the coefficients. When you take in the end the, so you can show that you can rewrite your function in this way. It's 1 over s plus 1 plus 2 over s plus 1 to power 3. Now why is this interesting? Well, the inverse Laplace transform of this we've seen. This is the exponential to minus t. We've seen this before. But this we haven't seen before. So this would be, t squared times exponential to minus t, this with the 2. So, you basically have time squared multiplying the exponential. Typically, when you have repeated poles, like in this case, you will get terms of this sort, right? If the pole was complex conjugate, you would have here maybe exponential function times some sine or cosine function. So you might have t squared or t to the power 3 times sine times exponential. All right. So that's basically the inverse Laplace transform for this particular function. All right. All right, are there any questions? All right. Well, thank you again for coming. Please talk to your friends, and encourage them to come. I will send an email because it doesn't make sense to have these sessions if, the numbers. By the way, I've seen it's like a geometric series decaying, right? So there was I'm dividing by 2 every week. So, which maybe the recorded lectures are good enough and people can follow them, but I would prefer to have you here and you can ask me things directly. All right, thank you very much.
So why I cannot assume this one as because I think this can rewrite to s squared times 1 over s squared plus 1, and this may be the square of the differential of sine t function. So because this is the Laplace transform of sine t, right? And if I times the square of s, that means I do 2 differential for the sine t in the time domain, right? Why cannot assume
you are making a mistake. I'm just sort of not sure where. So let me just see. So we have to go out. There's another lecture. So let's just go out and we can take it aside.
Yes. He always come around this warning.
Yeah,
I don't know why.
this one that is
小孩子，然后让他